This is a network science course, and today we are going to study the 12th chapter of Mark Newman's book, which is about random graphs, and in particular the discussion is going to be about Erdős-Rényi random graphs. So this was the first mathematical model for random graphs back in like 70 years ago, roughly 60-70 years ago, and for a long time that was the only random graph model, proper random graph model in mathematics and well, in graph theory. But before going there, we need to take a tour into statistics and some recap about certain distribution functions. First of all, we need to start off with binomial distribution, which is, you might be familiar with it, but nevertheless it has two parameters, n and p, and it's a discrete probability function, and it measures the number of successes in a sequence of n independent yes or no experiments, so binary experiments. And we are interested that the probability is set up to be p, and then the success or failure of this experiment. There is a typo here on the slide. At this small n should be capital N. So the binomial distribution is usually denoted by bin n and p, and then with n we set up the number of trials, and then p is the success probability in each trial. Now a very basic and straightforward example: when we toss a coin and the coin is unbiased, so the p is equal to 0.5, and then we count how many times, the number of times the toss comes to be head. Now in this slide you can see a visualization of the binomial distribution for different p values, and in this case n was set up to be 20. Sometimes this is denoted by k, so don't get confused. And then you can see here that we get different distribution, okay, in case of different p values, and you can also see that that, for example, if we did 20 different try, for example, tossing a coin in which we can assume that p is equal to half, then half of the cases, so 10 times so the probability that we get head, for example, 10 times is that has the highest probability. Okay, so getting 11 times or 12 times the head which we were expecting, it's possible, of course, but it has lower and lower probabilities. Okay, and the same for p equal to 0.9 or p equal to 0.1. The other distribution I want to mention is the continuous version of the binomial distribution, which is called Poisson distribution, and and it basically expresses the probability of a given number of events occurring in a fixed interval of time and or space, in case these events occur with a known average rate and independently from time. And the formula for this Poisson distribution is given here. I did not give the formula for the distribution in case of the binomial distribution because we will see it when we turn for the discussion for the Erdős-Rényi graphs. Okay, and so this is the same figure, but now for the distribution, so the probability distribution figure for the Poisson distribution, you can interpret it in the same way. Now in this case, instead of having discrete values, we have continuous values, and these dots here, they are not representing any discrete values. It's just here for distinguishing the three lines. Okay, so kind of coloring. Now, if we compare two distributions, namely the binomial, the Poisson, and a normal distribution, then we know that they approach zero by exponential speed. Instead, if we see a power law degree distribution, power law distribution, I tend to say degree distribution because that's the corresponding, that's the relevant expression here for network science. So power law distribution, then they are definitely different from binomial, or well, in particular Poisson and normal distribution. And so it can be visualized, the difference, for example, like here, where the power law distribution is denoted as Pareto. So you can see that the Pareto, so the power law distribution for the visualization, so for the distribution function, it's not it's not approaching zero in exponential speed, but we have this long tail part, as we discussed in the previous lecture. And just as a side note, so this Pareto is coming from the famous Italian economist Vilfredo Pareto, who noticed that 80% of Italy's land was owned by 20% of the population in the time when he was active. And of course, it's maybe even worse today, not only in Italy but everywhere in the world. And since then, this is called as 80-20 rule. And this was one of the first applications or real world scenario when this power law degree distribution appeared and was kind of discovered. Another discussion and visualization is about comparing normal distribution with power law distribution. And well, the normal distribution, for example, it appears in the heights of people or speed of cars, and taking the example of heights of people, or in this case only males, it doesn't matter. According to the books of records, at least in some years in the past history, it doesn't matter the actual numbers now, but the tallest man at that time on Earth was 2 meters 72 centimeters, and the shortest man was 57 centimeters tall. Now the ratio between these two numbers, so if I divide these two numbers, what I get is 4.8. So the ratio of the extreme case is 4.8. Instead, if we take a histogram of the cities in the US by their population, so the number of inhabitants in the cities, then according to the statistics made in 2000, New York City was the largest city in the US with 8 million inhabitants, and the smallest city was somewhere in Virginia with 52 inhabitants. And well, the interesting thing here that if we take the ratio between these two numbers, then we get 150,000. So that's way much bigger than the 4.8%. Okay, so this is also a demonstration about the fact that normal distribution and also of course Poisson distribution is definitely different from power law distributions. And well, we tend to see that power law distributions are everywhere. So in this slide and in the following, you can see some interesting and sometimes funny examples of cases when power law distribution appears. For example, word frequency in a book about Moby Dick. So in this case we are counting that a particular word, how many times it appears, and then it turns out that this is going to be power law. Papers, citation of papers in a certain time frame, it also follows power law. Earthquake magnitudes in California or phone calls received. And in the next slide, well, I'm tired of listing all of these examples. So power laws are everywhere seemingly, but as a last slide for the introductory part before we start discussing the today's part about random graphs, not everything follows power law, of course. So funnily again, birth occurrences of different type or number of users in email address books or sizes of forestry, they are not following power law. So, but many networks and real world scenarios we find power law distribution. Okay, and this is going to be an important thing for the forthcoming graph model.